Before the 13th century, doing math meant writing essays. If an ancient scholar wanted to figure out an unknown quantity, they had to write out the entire problem in long-form prose, detailing every step in complete sentences without a single plus or equal sign. Civilizations like the Babylonians developed complex numerical tracking 3,000 years ago, but across different regions, there was no agreed-upon shorthand for mathematical operations or missing values. This bottleneck broke with the 9th century Islamic mathematician Al-Khwarizmi. Working in Baghdad, he wrote a highly practical treatise on balancing unknown quantities. His text introduced the systematic approach to solving equations we still use today, and gave us the word algebra itself. Over the following centuries, mathematicians replaced those clunky paragraphs with a tight, symbolic shorthand. This allowed the human mind to stop getting bogged down in the syntax of a sentence and start seeing the underlying structure of a problem. To read this structural shorthand, you need to understand its basic alphabet. The core of algebra is the variable, a specific letter, like X or Y, standing in for a quantity that we either don't know yet or one that can change. Surrounding variables are strict modifiers. Constants are fixed numbers, and coefficients are multipliers attached directly to the variable. Combine these pieces without an equal sign, and you get an expression. But once you state this expression equals something else, it becomes a solvable equation. Translating messy, real-world variables into this strict symbolic alphabet provides a standardized map to locate and identify hidden values. Just having symbols isn't enough. You need grammar. If you try to calculate a complex string of numbers and operations without a shared set of rules, you will end up with multiple, contradictory answers. To fix this, mathematicians follow a rigid hierarchy of operations. At the very top of this pyramid, you always resolve anything grouped inside parentheses first. Immediately after that, you evaluate the exponents, your powers and roots. The next layer down handles multiplication and division. These hold the exact same priority as each other, so you simply execute them in order from left to right. Finally, addition and subtraction share the foundation, again worked across from left to right. Sticking strictly to this order ensures that whether an equation is being solved by a student in Tokyo or a server farm in California, everyone arrives at the exact same reproducible result. When analyzing these equations, it helps to rethink the equal sign. Instead of reading it as a command to compute an answer, treat it as a rigid statement of perfect balance between the left and right sides. The entire goal of solving a linear equation is to sort this balance system. You want to manipulate the statement until all the unknown variables are clustered on one side and all the known constants are pushed to the other. You achieve this by applying inverse operations. If a constant is being added to your variable, you subtract it. If it's being multiplied, you divide. And to maintain that perfect equilibrium, whatever operation you apply to one side, you must immediately apply to the other. By systematically stripping away the coefficients and constants step by step, you eventually isolate the variable completely, revealing its exact numerical value on the opposite side of the scale. This application of inverse logic unmasks an unknown value by stripping away its surroundings without compromising the system's stability. Real-world data rarely relies on a single unknown. Often, you face systems of linear equations, scenarios where two or more distinct mathematical sentences share the exact same set of variables at the same time. To crack these, you have to reduce the number of unknowns. One approach is the substitution method. You isolate a single variable in the first equation, then plug that resulting mathematical phrase directly into the second equation as a replacement. For more complex setups, you can use the elimination method. By multiplying and then directly adding or subtracting entire equations together, you can force identical variable terms to completely cancel each other out. Collapsing a multivariable system down to a single unknown brings order to complex data, allowing us to extract precise answers from layers of overlapping information. Once you master this logic, you start to see it operating everywhere. The ability to isolate and manipulate unknown variables is the engine driving our financial forecasting, allowing analysts to balance global budgets and predict economic market swings. Proportional algebraic thinking dictates how physical materials scale. It tells an architect exactly how much steel to add when expanding a construction blueprint from a modest structure to a towering skyscraper. When you pull out your phone for directions, routing algorithms rely on continuous algebraic calculations of distance, speed, and time to pinpoint your arrival. Beyond everyday logistics, advanced algebraic matrices are used to encrypt our sensitive data, adjust weights within artificial intelligence models, and calculate precise, life-saving pharmacological dosages. It acts as an invisible scaffolding, a rigorous set of rules that takes the chaotic, unpredictable variables of the physical universe and snaps them into solvable, actionable truths. For early human civilizations, physical reality was a landscape of shifting borders. When seasonal floods washed away landmarks, a community's ability to precisely measure its land determined its survival and its food supply. The word geometry itself originates from the Greek terms for earth and measurement. In its earliest forms, it functioned as a practical set of techniques for land surveying and architectural construction. Civilizations from Mesopotamia to Giza used these empirical methods to divide land and align massive monuments with incredible precision. However, these ancient surveyors relied on localized, practical rules. They knew which techniques worked for a specific building or field, but they lacked a unified theory to explain why those shapes behaved consistently across the entire natural world. This changed when Greek philosophers began to treat geometry as an intellectual pursuit rather than a craft. Thales of Miletus is credited with moving the field away from simple observation and toward deductive reasoning and abstraction. Around 300 BCE, Euclid of Alexandria collected these emerging theorems into a single 13-volume treatise called The Elements. He organized the knowledge of his predecessors into a formal, interconnected system. Euclid's approach was based on the axiomatic method, starting with a few self-evident truths to prove complex results. Centuries later, Albert Einstein noted that this level of logical lucidity made an indescribable impression on him, as the assertions could be proved with a certainty that left no room for doubt. By establishing this rigorous framework, Euclid set the standard for mathematical proof that would dominate geometric education for over 2,000 years. Euclid's system is built upon three undefined terms, primitive notions that are so basic they are accepted without a formal definition. The first is a point, a precise location in space with no dimension. A line has one dimension, consisting of infinite points extending forever. A plane adds a second dimension, a flat surface with length and width stretching infinitely. These three abstractions, points, lines, and planes, formed a conceptual bedrock. Without these impossible starting points, the physical measurement of our world cannot begin. As this chart illustrates, two-dimensional polygons are formed when three or more straight lines are bounded together in a plane to enclose a specific area. When several of these planar surfaces are folded and combined, they extrude into three-dimensional solid shapes, like prisms and pyramids, characterized by their height, breadth, and depth. This progression from abstract lines to solid volumes is what allows geometry to describe the tangible objects of our physical universe. Within this structured space, shapes are governed by laws of interaction. This begins with the relationships between angles created by intersecting lines. These relationships allow us to solve for missing measurements. For example, complementary angles always add up to 90 degrees, while vertical angles, those opposite each other at an intersection, are always equal. This leads to congruence. Two congruent shapes are identical in every way, sharing exact side lengths and angle measures. In contrast, shapes are similar if they share the same proportions and angles, but have different sizes. One is a scaled version of the other. These rules ensure spatial logic remains consistent. Whether a shape is centimeters wide or kilometers across, the mathematical relationship between its parts never changes. Geometric laws also dictate how objects move through space using mathematical transformations. Rigid motions, like the translations and reflections shown at the top of this diagram, move a shape without altering its size or form. Non-rigid motions, such as the dilation shown below, enlarge or reduce an object while preserving its similarity. By applying these transformations to coordinates on a plane, we can mathematically define every possible movement of an object through space. While these axioms are over 2,000 years old, They function as the literal engine powering modern spatial technology. Global positioning systems track our real-world location by calculating the intersection of spheres in a network, a macro-scale application of 3D geometric trilateration. In the digital world, animation and game studios use these same principles through a process called polygonal modeling. Here, Euclid's terms are executed by code. Vertices are points in 3D space. Two vertices joined by a line become edges, and three or more edges define the 2D faces of a shape. Thousands of these geometric faces are linked by shared vertices to form complex 3D meshes that represent people, animals, or environments. Modern ray tracing algorithms then simulate photorealism by mathematically calculating how light vectors bounce off these exact geometric faces. Digital reality is essentially the massive, high-speed execution of ancient geometric logic. Geometry serves as the structural language through which we understand space and the physical universe. This axiomatic logic provided the initial framework for humanity to measure and manage the world we inhabit.
In 1794, Thomas Paine observed that the scientific principles used to direct the course of a ship on the ocean or to predict the motion of the heavenly bodies were rooted in one discipline. He called trigonometry the soul of science. For early explorers, making sense of a massive, imposing world required the basic geometry of right triangles. By measuring the angles between themselves, the horizon, and the stars, they could pinpoint their exact location on an otherwise featureless sea. This ambition to measure the Earth reached its peak in the 19th century with the Great Trigonometrical Survey of India. Mathematicians and geographers triangulated vast distances across the country, creating a massive geometric network. This survey allowed mathematicians to calculate the precise height of Mount Everest from hundreds of miles away, a feat achieved without ever climbing the mountain. In this era, the triangle served as humanity's ultimate ruler. It allowed us to map a static physical world, shrinking impossibly large natural obstacles down into quantifiable, manageable distances. While those triangles captured a moment in time, the physical universe exists in a state of constant motion, oscillation, and rotation. Standard right-angle calculations, like the SOH-CAH-TOA ratios, lose their utility when trying to measure a system that refuses to hold still. Mathematicians bridged this gap by locking a right triangle to the center of a circle with a radius of 1, the unit circle. As the triangle rotates, its vertical side smoothly stretches and shrinks. Plotting this changing height creates a continuous sine wave. By placing the triangle inside a circle, trigonometry escapes the confines of static geometry. It becomes the mathematical language of continuous waves. Modern engineers apply this mathematical language to model the continuous, dynamic forces acting on physical structures. When designing massive suspension bridges, engineers use trigonometric functions to calculate the precise angles of tension, keeping the structure from collapsing. These same principles allow designers to calculate the wind load sway of extreme skyscrapers, ensuring even the tallest buildings maintain their center of gravity. Beyond structural stability, trigonometry enables the creation of perfectly controlled, precise movement. Robotic manipulator arms rely on continuous trigonometric equations to execute millimeter-perfect joint rotations in three-dimensional space, a field known as kinematics. Trigonometry serves as the invisible mathematical scaffolding of modern engineering, translating abstract physics into stable structures and exact mechanics. This scaffolding extends into the invisible waves of energy powering the modern electrical grid. Our homes are powered by alternating current, where the electrical charge rapidly reverses direction inside the wires to deliver power reliably. Electrical engineers use the exact same trigonometric wave derived from the unit circle to perfectly model this flow of voltage and current. Every time you flip a light switch, you are utilizing an invisible wave dictated by the geometry of a rotating triangle. This periodic motion defines the foundation of what we hear. A single musical note is simply a mechanical sine wave traveling through the air. In the real world, sound is rarely pure. The noises of a symphony or a bustling city are chaotic, jagged, and complex. However, Joseph Fourier discovered that any complex wave is actually just a stack of simple sine and cosine waves. This process, Fourier analysis, allows us to deconstruct even the most chaotic sounds into their trigonometric layers. The universe reveals its hidden order through these layers. Its most complex phenomena are just simple trigonometric patterns stacked together. Our own biology is built to interpret these mathematical layers. Inside the human ear, the basilar membrane is constantly bombarded by complex pressure waves from the environment. The human ear naturally performs its own physical Fourier analysis, unstacking complex noise into simple frequencies to send clear electrical signals to the brain. Thomas Paine's profound assertion that trigonometry is the soul of science captures its reach across the massive scale of astronomy and the microscopic scale of our senses.
If you want to calculate the average speed of a car blurring past you on the highway, basic algebra does the trick perfectly. You simply take the total distance traveled and divide it by the total time it took. But what happens if you want the exact speed of that car at a single frozen millisecond? The elapsed time is 0. The distance traveled in that exact instant is also 0. You are left with 0 divided by 0. At this scale, algebra breaks down entirely. The physical universe is in constant fluid motion. Planets orbit, apples fall from branches, and arrows fly through the air. But traditional mathematics was trapped in static states, only capable of measuring fixed snapshots in time. To measure continuous change, humanity required an entirely new mathematical language. We needed a system specifically designed to unfreeze time. From opposite ends of Europe, Newton and Leibniz had independently forged the tools needed to finally solve the paradox of change. Newton approached the problem through the lens of physical motion. He called his system the method of fluxions, focusing on how continuous quantities, like position or velocity, flowed over time. This graph shows how we traditionally measure speed. We plot a curve representing position over time, and draw a straight line, a secant line, between two distinct points. The slope of that line gives us the average speed between them. To find the speed at a single instant, Newton imagined what happens if we slide those 2 points closer and closer together, shrinking the distance between them until it approaches 0. When those points merge, the secant line becomes a tangent line. It touches the curve at exactly 1 point, perfectly skimming the edge. The slope of this new line is the exact mathematical rate of change at that specific moment. This concept is the derivative. It bypasses the 0 divided by 0 paradox entirely, allowing us to calculate the exact velocity of an object at a single frozen instant. While Newton looked at motion, Leibniz focused on geometry. He developed a highly visual approach, introducing the elegant elongated S notation that we still use today. This graph demonstrates Leibniz's method for finding the total area accumulated under a curve. He started by filling the space beneath it with a series of measurable vertical rectangles. You calculate the area of each and add them up for a rough estimate. To get a more precise measurement, you make the rectangles thinner. Then, logically, you push this to the absolute extreme. You make them infinitesimally thin, creating an infinite number of rectangles that seamlessly pack the space. The sum of this infinite series gives you the exact area. This geometric accumulation is called the definite integral. By summing up endless tiny slices of data, the integral acts as the ultimate tool for measuring how continuous changes accumulate over time. The grand irony of the 17th century priority dispute is that Newton and Leibniz were brutalizing each other over 2 halves of the exact same truth. Their discoveries are united by the fundamental theorem of calculus. It connects the concept of instantaneous change directly with the concept of infinite accumulation. This animated graph illustrates the connection. As we track along the horizontal axis, the shaded area under the curve expands, representing continuous accumulation. Look closely at how fast that total area is growing at any given second. By highlighting the leading edge, we can see that the exact rate at which the area expands is equal to the current height of the curve itself. The derivative of the area gives you the curve, and the integral of the curve gives you the area. They are perfect mathematical inverses. Newton's frozen instants and Leibniz's infinite accumulations are inextricably linked. Both men relied on a conceptually shaky idea in their original work. They used infinitesimals, infinitely small, non-zero quantities that were heavily criticized at the time as illogical ghosts of departed quantities. It took subsequent generations of mathematicians to fix this flaw. They replaced infinitesimals with the rigorous concept of limits, creating a solid logical framework to explain how a value can be approached without quite reaching it. This rigorization phase took the brilliant, intuitive leaps of two fierce rivals and forged them into an unbreakable mathematical foundation for modern science. That unified theory allows astrophysicists to predict the dynamic orbital trajectories of spacecraft as they navigate the constantly shifting gravity wells of planets. Civil engineers rely on the same mathematics to calculate fluctuating tension gradients in monumental infrastructure, ensuring suspension bridges can withstand high winds and heavy traffic. In the biological sciences, it models cyclic predator-prey dynamics and maps the exact rate at which a drug decays in the human bloodstream. Newton largely won the battle of reputation in his lifetime, while Leibniz's superior notation won the long war of practical use. To model reality, whether you are tracking the orbit of a planet or predicting a global financial market, you have to calculate hundreds, sometimes thousands, of interconnected variables at the exact same time. Nearly 4,000 years ago, Babylonian scholars attempted to track these multivariable systems by solving simple 2x2 grids of equations carved directly into clay tablets. But as civilization scaled up, so did the math. The sheer number of variables required to map the physical world quickly outpaced what simple arithmetic could handle. By the Enlightenment, scientists like Carl Friedrich Gauss measured the exact curvature of the Earth, wrestling with unreadable tangles of simultaneous equations. Without a unified way to organize these calculations, scientists were reaching the limit of what manual arithmetic could achieve. Every new variable added to a system made the math significantly more difficult to solve. In 1848, James Joseph Sylvester began imposing structure on these variables, consolidating the coefficients from sprawling equations into a single structured grid of numbers. Sylvester called this grid a matrix, drawing from the Latin word for womb. He saw it as a generative container, a mathematical structure that gave birth to solutions and patterns that were previously hidden. A few years later, Arthur Cayley took Sylvester's container and proved something new. These matrices were distinct mathematical objects of their own, complete with rules allowing them to be multiplied and manipulated. Treating a grid of numbers as a single object meant that abstract algebraic equations no longer had to remain abstract. They could now be treated as aggregate objects rather than lists of individual coefficients. The matrix changed the scale of calculation. By treating a collection of variables as a single object, mathematicians could begin manipulating entire systems at once, rather than solving for one variable at a time. A matrix operates as an active engine of linear transformation. It physically alters the very space it inhabits. This diagram shows a standard two-dimensional coordinate system. When you multiply this physical space by a matrix, the numbers inside that matrix force the entire space to warp, stretch, rotate, or shear. Every single intersection point on the original grid is forced to move to specific new locations. To understand what just happened to our space, we use a measurement called the determinant. The determinant is the master scaling factor, a single number that tells you exactly how much the transformation stretched or squished the total volume of that space. If a matrix has a determinant of exactly 0, the entire physical space collapses into a lower dimension. The area vanishes, and the information is permanently destroyed. The determinant is the critical diagnostic tool for any system. It provides the exact factor by which a transformation expands, compresses, or collapses the geometry of a coordinate space. This animation illustrates the central spatial problem of these transformations. When a matrix warps a coordinate system, almost every vector is knocked completely off its original directional path. But there are exceptions. We call them eigenvectors. These are the specific arrows that maintain their exact original direction, even as the space around them twists and shears. While their direction stays fixed, their length often changes. The specific numerical amount these vectors are stretched or compressed during the transformation is known as their eigenvalue. Identifying these fixed anchors within a transforming system isolates the core structure of a complex model, even when the data shifts. Because Cayley and Sylvester successfully turned abstract algebra into geometry, modern engineers can teach computers how to manipulate multidimensional space. Computer graphics and 3D rendering rely entirely on this translation. Every movement you see on a screen is the result of millions of matrix multiplications, rotating coordinates in space 60 times a second. Machine learning and big data algorithms run on these exact same matrix transformations to compress millions of dimensions of human behavior into manageable, predictable patterns. The physical universe operates on this math as well. In quantum mechanics, eigenvalues represent the literal, stable energy states of atoms. Linear algebra is the invisible architecture that renders our digital universe, trains artificial intelligence, and decodes the quantum realm.